Something is very wrong with this visitor from beyond. 3I Atlas, the third confirmed interstellar comet ever recorded, just passed through its closest approach to the Sunday. And what space-based observatories witnessed during that passage has left scientists searching for explanation. The coma turned blue, intensely, unmistakably blue. When most comets glow reddish or greenish, 3I Atlas shifted to a coloration that indicates chemistry we rarely see. Chemistry that suggests composition fundamentally different from objects native to our solar system. The brightness surged, not gradually following thermal models as solar heating increased, explosively, rapidly, in ways that suggest either massive outbursts, structural failure, or exposure of materials that shouldn't be accessible at this stage of the comet's passage. And the tail pointed wrong. Cometary tails follow predictable geometry, sculpted by solar radiation and solar wind. 3I Atlas tails showed orientations that don't match those patterns. Orientations that suggest either unusual dust properties, abnormal rotation, or forces acting on the nucleus that our models don't account for. Ground-based telescopes couldn't observe the comet during its perihelion passage. Solar glare makes Earth-based observation impossible when objects pass too close to the Sun. But space-based solar monitoring satellites maintain coverage. SOHO, Stereo A, and GOES-19 all tracked 3I Atlas through its closest solar approach. What they documented challenges fundamental assumptions about how comets behave. Each anomaly individually might be explainable. Together, they create a profile unlike anything in our observational database. Scientists are now analyzing the data. Models are being revised. Observation campaigns are tracking the comet's outbound journey to see whether the strange behavior continues or whether perihelion was a singular event that won't repeat. Because when an interstellar visitor displays three major anomalies simultaneously, when it violates multiple predictions at once, understanding why becomes critical not just for this object, but for every future visitor we'll encounter from beyond our solar system. Understanding what makes these observations so significant requires understanding the challenge of observing comets during perihelion passage. When any object passes close to the Sun from Earth's perspective, solar glare overwhelms the faint light reflected or emitted by that object. Ground-based telescopes, no matter how powerful, cannot observe through the Sun's brilliance. Even pointing a telescope near the Sun risks damaging sensitive instruments. Professional observatories implement strict pointing limits that prevent telescopes from aiming within several degrees of solar position. This creates an observational blackout. For days or weeks, depending on the comet's trajectory and perihelion distance, ground-based astronomy goes blind. The most critical phase of a comet's passage, when solar heating reaches maximum intensity and activity peaks, occurs precisely when Earth-based observation becomes impossible. 3I Atlas perihelion occurred at approximately 0.5 astronomical units from the Sunday, roughly half Earth's distance. That placed it well within the ground-based observation exclusion zone for over a week. But space provides alternatives. Solar observatories orbiting Earth, or positioned at gravitationally stable points, carry instruments designed specifically to observe the Sun's immediate environment. These spacecraft use occulting disks, physical barriers that block the Sun's direct light, creating artificial eclipses that allow observation of the surrounding space. SOHO, the Solar and Heliospheric Observatory, has operated since 1995. Its LASCO coronagraphs have discovered over 4,000 comets passing near the Sun, mostly small sun-grazing comets that vaporize during closest approach. But LASCO can track any object passing through its field of view. Stereo A, part of NASA's Solar Terrestrial Relations Observatory mission, provides complementary viewing angles. Positioned ahead of Earth in its orbit, Stereo A sees the Sun from different perspectives than Earth-based or Earth-orbiting observatories, allowing three-dimensional reconstruction of solar phenomena and objects passing near the Sunday. GOES-19, primarily a weather satellite, carries solar monitoring instruments that captured additional data on 3I Atlas during perihelion. While not designed for cometary observation, its sensors detected the brightness and spectral changes as the comet passed through its field of view. These three platforms maintain continuous coverage throughout 3I Atlas perihelion passage. Their combined observations documented behavior that would have remained completely unknown without space-based monitoring. Subscribe now, because what these satellites revealed might force us to reconsider everything we thought we understood about interstellar comets. The first major anomaly is color. During perihelion passage, 3I Atlas coma shifted to intense blue. This is highly unusual. The vast majority of comets appear reddish, yellowish, or greenish, depending on composition and activity levels. Cometary color comes from molecular emissions and dust scattering. When solar ultraviolet radiation strikes molecules in the coma, those molecules absorb energy and re-emit it at specific wavelengths characteristic of their chemical structure. Water vapor and its breakdown products, hydroxyl radicals and hydrogen atoms, create reddish and greenish emissions. Dust particles simply reflect sunlight, appearing yellowish or white depending on grain property. Blue coloration indicates specific chemistry. The most common source of blue light in astronomical objects is ionized carbon monoxide. When carbon monoxide molecules lose electrons due to intense solar radiation, the resulting positively charged ions emit strongly in blue wavelengths. Additionally, certain carbon-based molecular fragments called radicals can produce blue emission. The intensity of blue in 3I Atlas suggests unusually high carbon monoxide activity. This would be consistent with interstellar origin. Carbon monoxide is a hypervolatile ice, meaning it sublimates at temperatures far below water ice. A comet rich in carbon monoxide would show activity at greater solar distances than water-dominated comets and could produce more vigorous outgassing when finally heated to higher temperatures near perihelion. But the timing creates questions. If 3I Atlas is carbon monoxide rich, why did blue coloration become prominent specifically during perihelion rather than appearing gradually throughout the approach? Carbon monoxide should have been sublimating continuously as the comet moved inward. One explanation: subsurface reservoirs. Perhaps carbon monoxide deposits existed beneath insulating surface layers. As the comet approached perihelion, heat conducting through those layers finally reached the carbon monoxide ice. Once temperature crossed the sublimation threshold, the buried ice began transitioning to gas rapidly. Pressure built beneath the surface. Eventually, the overlying crust fractured, allowing explosive release of carbon monoxide that had accumulated below. This scenario predicts that the blue coloration should be temporary. As the comet recedes from perihelion, as temperatures drop and the exposed carbon monoxide depletes, the blue should fade. Early post-perihelion observations confirm this prediction. The intense blue visible during closest solar approach has already diminished as 3I Atlas moves outward. Another explanation involves temperature-dependent chemistry. Perhaps 3I Atlas contains carbon-rich compounds that only break down into blue-emitting fragments at the extreme temperatures near perihelion. These compounds remain stable farther from the Sun but decompose when heated sufficiently, releasing carbon monoxide or other blue-emitting species. Spectroscopic analysis will determine which molecules are actually present and in what abundances. But the blue coloration already tells us that 3I Atlas chemistry differs significantly from typical solar system comets, which are predominantly water ice with smaller fractions of other volatiles. The second anomaly is brightness behavior. 3I Atlas brightened far more rapidly during perihelion than thermal models predicted. This wasn't gradual intensification as sublimation increased with solar heating. This was explosive, suggesting sudden events rather than steady thermal response. Cometary brightness depends on how much material fills the coma, reflecting sunlight and emitting molecular fluorescence. Standard models calculate expected brightness based on several factors: distance from the sun, which determines solar heating intensity; nucleus size estimates, which determine total surface area available for sublimation; and typical activity coefficients derived from observing thousands of solar system comets. For 3I Atlas, these models predicted modest brightening through perihelion. The comet should have gradually increased in brightness as solar distance decreased, peaked near closest approach, then gradually faded as it receded. The observed brightness deviated dramatically from these predictions. Within days around perihelion, 3I Atlas brightened by factors suggesting either a much larger nucleus than initial estimates, far higher activity rates than typical comets show at this distance, or sudden discrete events like major outbursts or fragmentation. Outbursts occur when subsurface volatile ice deposits suddenly sublimate. Internal pressure builds until surface material can no longer contain it. The crust fractures or explodes outward, releasing accumulated gas and entrained dust in a rapid burst. These events can temporarily increase cometary brightness by factors of 10 or more before activity returns to baseline levels. Fragmentation produces similar brightness increases, but through different mechanisms. If thermal stress or rotational forces cause the nucleus to split, fresh internal ice suddenly becomes exposed to direct sunlight. These pristine surfaces, lacking the protective dust layer that gradually builds up on comet surfaces, sublimate vigorously when first heated. Distinguishing between outburst and fragmentation requires careful analysis of how brightness evolves after the event. Outbursts typically show rapid rise, followed by exponential decay back to pre-outburst levels as the released material disperses and activity returns to normal. Fragmentation shows brightness increase that may not fully decay if separated fragments continue contributing to total brightness. Additionally, fragmentation should produce visible evidence of multiple nuclei if fragments separate sufficiently. High-resolution imaging of 3I Atlas in coming weeks will search for signs of splitting. The brightness explosion during perihelion, combined with the blue coloration, paints a picture of violent activity. Material venting from the nucleus at high rates, internal processes releasing stored volatiles explosively. The comet responding to solar heating in ways that exceed predictions based on local objects. Comment below. If you could ask one question about 3I Atlas that would be answered immediately, what would you want to know? The third anomaly is tail orientation. Cometary tails have predictable geometry determined by well-understood physics. Solar radiation pressure pushes dust particles outward from the sun, creating curved dust tails. Solar wind, the stream of charged particles flowing outward from the sun, drags ionized gas molecules along magnetic field lines, creating straight ion tails pointing directly away from the sunday. 3I Atlas tail geometry during perihelion didn't match these standard patterns. Solar observatory images show tail structures pointing in directions that simple models don't predict. The orientation suggests either unusual properties of the dust and gas being released or forces acting on the comet that alter how material leaves the nucleus. Several explanations exist for anomalous tail geometry. The simplest involves rotation and jet directionality. If 3I Atlas nucleus rotates with active regions concentrated in specific locations, material released from those regions carries momentum in particular directions. As the nucleus spins and orbits simultaneously, these directional jets create tail structures that don't align with simple radial from sun geometry. This explanation requires specific conditions. The rotation axis must be oriented such that jets point in directions that create visible tail distortions. The jets must be powerful enough that their momentum dominates over radiation pressure and solar wind effects. And the viewing geometry must allow Earth-based or space-based observers to see the resulting tail structure clearly, rather than viewing it edge-on or from angles where the effect is minimized. Another explanation involves unusual dust properties. If three I-Atlas dust particles have different size distributions or compositions than typical cometary dust, they might respond differently to radiation pressure. Very small particles experience stronger radiation pressure relative to their mass. If 3I Atlas is producing predominantly small grains, those grains would be pushed more strongly, creating tail structures with different curvature than expected. A more concerning explanation involves trajectory deviations. All tail geometry calculations assume the comet follows a gravitational orbit determined solely by the Sun's gravitational pull and minor perturbations from planets. If 3I Atlas is experiencing non-gravitational forces, if its actual path through space differs from gravitational predictions, then tail structures calculated assuming the predicted path would appear anomalous. Non-gravitational forces on comets come primarily from outgassing. Gas venting from the nucleus carries momentum. By Newton's third law, the nucleus experiences reaction force in the opposite direction. For typical comets, these forces are well characterized and can be included in orbital calculations. But if 3I Atlas outgassing is far stronger or more asymmetric than typical, non-gravitational forces might be larger than models account for. Resolving this requires precise astrometry after perihelion. Measuring exactly where 3I Atlas appears in coming weeks and comparing those positions to gravitational predictions will reveal whether trajectory deviations are occurring. If observed positions match predictions within measurement uncertainty, the tail anomaly is purely structural or rotational. If positions show systematic offsets, real non-gravitational acceleration is operating. One framework for understanding all three anomalies simultaneously is unusual composition. If 3I Atlas formed in a stellar environment fundamentally different from our solar system, its ice mixture might bear little resemblance to local comets. Stars vary enormously in their properties. Mass, age, metallicity, and evolutionary state all affect the protoplanetary disks that form around them. A comet forming around a young, metal-poor red dwarf would experience completely different conditions than one forming around our middle-aged solar metallicity Sunday. Temperature profiles in protoplanetary disks depend on stellar luminosity. Lower mass stars produce less heat. Their disks remain colder at equivalent distances than our solar system's disk was during formation. In these cold environments, highly volatile ices like carbon monoxide and nitrogen dominate over water ice in the outer regions where comets form. If 3I Atlas originated in such a system, it might contain ice ratios dramatically different from solar system comets. High carbon monoxide, high nitrogen, possibly high methane and other organics, with water as a minor rather than major component. This compositional difference would explain the blue coloration. Carbon monoxide sublimating and ionizing produces blue emission. It would explain the vigorous activity driving rapid brightness increases. Hypervolatile ices sublimate more readily and produce stronger outgassing per unit surface area than water ice. And it might contribute to tail anomalies if the gas and dust properties differ from materials we're accustomed to observing. But composition alone doesn't easily explain all observations unless combined with structural properties. The explosive brightness surge suggests discrete events like outbursts or fragmentation, which involve structural failure rather than just composition-driven activity. An alternative framework interprets the anomalies as evidence of structural weakness if 3I Atlas has low internal cohesion. If it's essentially a loosely bound pile of smaller fragments held together by weak gravity and frozen ices, thermal stresses during perihelion could trigger dramatic responses. Thermal stress comes from temperature gradients. Solar radiation heats the sunlit side of the nucleus. The shadowed side remains cold. This temperature differential causes expansion on the warm side and contraction on the cold side. Materials with low tensile strength can't withstand these stresses and fracture. If 3I Atlas is structurally weak, perihelion passage might have triggered multiple fracture events. Cracks opening through the nucleus would allow rapid heat penetration to subsurface ices. This would accelerate sublimation dramatically, creating the observed brightness surge and potentially exposing carbon monoxide-rich deposits that produce the blue coloration. Major fracturing could also explain tail anomalies. If large sections of the nucleus separated slightly without completely fragmenting, each section would vent material somewhat independently. The combined effect of multiple active regions on partially separated components could create complex tail structures that don't match simple single nucleus models. This framework makes testable predictions. If 3I Atlas is structurally compromised, additional changes should occur over coming weeks and months. Brightness fluctuations as different fractured sections rotate into sunlight. Possible visible fragmentation if components separate sufficiently. Changes in rotation rate if mass distribution shifted during perihelion. Monitoring these potential changes will constrain which framework better explains observations. 3I Atlas has emerged from perihelion and is now receding outward from the Sunday ground-based observatories have regained line of sight now that the comet has separated sufficiently from solar glare. Intensive observation campaigns are tracking its post-perihelion evolution. Several key questions drive current observations. First, has brightness returned to pre-perihelion predictions, or does it remain elevated? Sustained high brightness would indicate permanent changes from perihelion passage, suggesting fragmentation or newly exposed volatile-rich surfaces rather than temporary outbursts. Second, has spectroscopic composition changed? Comparing pre-perihelion spectra to current observations will reveal whether the molecules being released have changed, which would indicate that different materials are now exposed or that thermal processing altered surface composition. Third, does precise astrometry show trajectory deviations? Position measurements over coming weeks will determine if non-gravitational forces acted during perihelion to alter the orbit measurably beyond gravitational predictions. Fourth, has coma morphology changed? High-resolution imaging will search for evidence of fragmentation, multiple brightness peaks that might indicate separated nuclei or altered jet patterns suggesting structural changes. Early results suggest 3I Atlas remains brighter than pre-perihelion models predicted. The intense blue coloration has faded as expected with increasing solar distance, but overall activity levels exceed predictions. This could indicate either that perihelion passage exposed new volatile-rich surfaces that continue outgassing, or that the nucleus fragmented and multiple components now contribute to total brightness. Definitive answers will emerge over coming months as data accumulates and analysis proceeds through peer review. But preliminary observations already indicate that 3I Atlas experienced significant changes during perihelion passage that distinguish it from typical cometary behavior. 3I Atlas reinforces a pattern emerging from interstellar object observations: extreme diversity. Each confirmed visitor from beyond our solar system has displayed unique characteristics. One, Oumuamua, showed no cometary activity whatsoever, despite predictions that it should outgas as it approached the Sunday. Yet it experienced non-gravitational acceleration that remains debated, with explanations ranging from invisible hydrogen outgassing to more exotic proposals. 2, Borisov behaved conventionally. Its composition matched solar system comets. Its activity followed predictable thermal response. It demonstrated that at least some interstellar comets form through processes similar to our local comet formation. 3I Atlas shows activity but with multiple anomalies: blue coloration, explosive brightening, anomalous tail geometry. It's neither inert like Oumuamua nor conventional like Borisov. It occupies new parameter space in our growing catalog of interstellar visitors. This diversity makes sense when considering formation environments. Our solar system represents one set of initial conditions. Billions of other stellar systems provide vastly different conditions, different stellar masses, different chemical abundances, different disk temperatures, different radiation environments. Objects forming under such varied conditions will naturally display varied properties. But this diversity complicates modeling and prediction. As more interstellar visitors are detected, as survey capabilities improve, and detection rates increase, we cannot assume they'll behave like objects we've studied before. Each requires individual characterization. Each must be understood on its own terms, rather than forced into categories derived from local experience. The Vera Rubin Observatory, beginning operations soon, will dramatically increase interstellar object detection rates. Predictions suggest dozens per year once the survey reaches full capacity. Each detection will require rapid follow-up to characterize composition, structure, and behavior before the object fades beyond observation. 3. iAtlas is teaching us how to approach this future. Expect surprises. Don't over-rely on models built from solar system objects. Maintain observational flexibility to capture unexpected phenomena. And recognize that diversity is information, not noise to be explained away. As I record this, 3 iAtlas continues outbound from the Sunday. The strange behavior observed during perihelion passage is being analyzed by research teams worldwide. Data is being shared across institutions. Models are being refined. Hypotheses are being tested against accumulating observations. The blue coma, the brightness explosion, the tail orientation anomalies, each represents a departure from standard cometary physics. Together they paint a picture of an object whose properties differ fundamentally from the thousands of solar system comets that have informed our understanding. Whether those differences trace to exotic composition from formation around a different stellar type, to structural properties altered during millions of years in interstellar space, to internal processes we haven't characterized, or to combinations of factors, the observations are expanding our frameworks. They're demonstrating that our models, while successful for local objects, don't necessarily generalize to visitors from different stellar environments. Scientists are being honest about uncertainty. They don't have complete explanations yet. The data is still being analyzed. Alternative hypotheses are being evaluated. This is exactly what discovery looks like: encountering phenomena that challenge existing understanding, proposing explanations, testing them rigorously, revising conclusions as evidence demands. 3. iAtlas is acting strange. It violated multiple predictions simultaneously during perihelion passage, and those violations are teaching us that interstellar comets aren't just fainter versions of local objects. They're fundamentally different, carrying chemistry and structure shaped by stellar environments we cannot directly observe, bringing us physical samples from places we cannot reach. The third interstellar comet may be strange, but its strangeness is exactly what makes it valuable. Every anomaly is information. Every violation of predictions is an opportunity to learn something new about how diverse planetary systems throughout the galaxy actually are. Comment below. Which explanation do you find most compelling? Unusual composition, structural weakness, or something we haven't considered yet? And subscribe, because 3 iAtlas observations continue, analysis proceeds, and as scientists work toward explanations for this strange visitor's behavior, we'll bring you updates on what they discover about the diversity of comets beyond our solar system. The comet that acted strange during perihelion is now revealing its secrets through post-perihelion observations. The data is accumulating, the answers are emerging, and somewhere in the measurements being collected right now, the truth about why this interstellar visitor behaved so unexpectedly is waiting to be found.